It's just a very brief introduction for those of you who haven't been part of part one, where we introduce business in a little bit more detail and also showed some use cases in the architecture. So my name is Susanne Maharos, and this is my colleague Martin Almeder, and we both work at the visualization department, the HLRS. This is just a brief overview of what we'll talk about, so I will very, very briefly introduce Vistle. And then Martin will do a live demo together with you guys, so you can create your first visualization with Vistle on the laptops. And then at the end, we will have an exercise where you visualize some open form data by yourself. So Vistle is a software for scientific visualization. And just very briefly, what is the motivation for visualizing scientific data? The first thing is to understand and contextualize, so put data into a context, abstract data and very large data. So the kind of data that we get every day from the people who are using a supercomputer, for example. There are researchers who work on simulation codes like you, but there are also companies or architects that come to us with their problem. Another reason is that you want a tool to analyze the data that you either measured or simulated or both of it at the same time. This is what we've seen in the cave demo where we combined different data sets together. It's also just a nice communication tool if you're working together in an interdisciplinary team or a remote team, something like that. So you can create either an image or a video that you can investigate together. And of course, just to present results to the public in a paper or in a presentation at a conference. And here on the right, the people who are in the cave seen this already. This is just the airflow simulation around the car that was done in a software Vistle. So basically, we visualize the velocity of the air as streamlines, which are the lines you can see here. And we've mapped the velocity with color as well. So the more it goes into red, the higher is the velocity at that point, and the more it goes into blue, the lower the velocity. Another typical way to visualize this data, but we will go through this in the live demonstration in the tutorial, is through the cutting circle, just the air pressure around the Vistle has been built after the so-called visualization pipeline, which is just a theoretical framework from visualization, and we put it here on the left. So the first step is always to acquire data. That can be through measurements, but most of the time in our case it's just through simulation. And in our software, it just means we have a reader where we can read in simulation results, for example. Then once you have the data inside, because the data sets are so large nowadays, you have to filter it so that you can look at the subpart of the data to make more sense of it more easily. And once you've done that, you can map the data to some sort of geometry, like a sphere or the lines that we just saw, or the plane, something like this. And then you render it to get an image that you can actually look at either on your desktop or in VR or AR. And yeah, then you have to display. And why we're mentioning this is because all of the modules that we have in Vistle, so a module is basically an independent program that does some kind of algorithm on the data. For example, it creates streamlines at one point. Or it reads in the data. All of them are categorized according to the steps in the visualization pipeline, but you will see this later more closely. And then on the right, you can see a screenshot of Vistle. So each of these rectangles is one of the modules I just talked about, and the modules can communicate with each other, so they can send data to each other. And to do that, you just simply draw the line. Hover is the renderer that we use, which works on a desktop, but it is specialized for virtual reality and for augmented reality. And here on the left, for the people who weren't in the cave demo, this was taken in our cave, which is basically a little room that you can walk into, and each of the walls, the ceiling, and the floor have a 3D image projected onto it, and then you have these 3D glasses on, so you actually see a 3D image. And you also have a little 3D mouse in your hand so that you can interact with visualization. And on the right is another example of AR, where we did an airflow simulation in an operation room and presented it at a supercomputing conference. Then there's also more advanced features of Vistle, which I just want to mention today. We're not going to go into it, just that you've heard about it. It's possible to write your own modules if you need like very specific algorithms for the data set that you have at hand. We are also working on making the modules run on the GPU right now. And there's also the possibility for in situ visualization. So it means that you visualize the result of a simulation while it is still running on a supercomputer. So you can look at the intermediate results if you want to. If you're interested into any of that, we have a documentation that we're actively working on. I put the link here, and I think we will share the slides after the workshop so you can check it out. With articles about that, and I mentioned the first seminar we had on Vistle at the beginning of the year. We also did a recording of that, so if you want to have a more general overview of Vistle, you can also check out. That's all I wanted to say about Vistle. I think we can get into a live demo now.
Yes. So I take over from here, and I think it's more not a demo, but a joint hands-on session. So I want you to perform the same steps that I do on your computers. Now we're going to start, and we're going to start by running Vistle. So we get a command line. You should find a terminal emulator at the bottom of your screen. Here on the left, you see my screen. Perhaps we switch screen to. So you open a terminal, and in the terminal, you type in Vistle in order to start Vistle. So that didn't go too well. I have to redo it. And we start by opening an existing workflow. So we navigate from the root directory to the installation directory of Vistle, and this is /mnt/RAID/soft/Vistle. And from there, we have some example workflows in the example directory, and we start with the simple airbag.txt. So I opened it by clicking on the open button here. I also could have used the menu and opened it here from the menu. And
Can you do the entire path again?
Yeah, I understand.
yes, sorry. And the entire path of the file that I opened
airbag
is
different.
do it again. It's /raid/soft/Vistle/example/airbag.esl. So I select airbag when I'm in this directory, mnt raid soft Vistle example, and I press the open button. And this loads new workflow.
Yeah. Right.
Apparently it doesn't work if you do it twice. So I take a shortcut and type it on the command line. But now we should be on the same page, and we should have this workflow open. We can execute this simple workflow, which consists of two modules. Here a reader for data in COVICE format, and the renderer cover, which opens this other window on your desktop. We go to the gears icon in the toolbar, press execute, and then it loads the data. And in order to get an overview of the data, this animation that is playing here, I choose this View All button to the right of the animation controls, and then it zooms out so that I can see all of the animation. And I can change the angle from which I view the animation by panning around with the left mouse button. So I can rotate the objects. I can zoom in and out with the right mouse button. And I can move around with the mouse wheel. So if I press the mouse wheel for the middle mouse button, I can move around. I can stop the animation by pressing the arrow at the top left. In the toolbar of the render window, and slide through the animation steps, or you can step through the animation here with the arrows. And initially, I'm in the smooth world interaction mode that we just used. And we can also switch to a drive mode where I fly within a plane and fly forward when I move the mouse forward, starting from the point where I start to click it, or move further away from the object when I move the mouse towards me. It's quite quick. Yes, you can adjust the speed with which this works from the navigation menu in the renderer window. There you have the drive speed. You can dial that down, and it should become a little bit easier to control. And depending on the size of the scene that you view, navigation is sometimes too fast and sometimes too slow. That's why you can just fit there. Okay, so this was a pre-configured workflow, but we want to learn how to build workflows ourselves. And we start with a new workflow. So we switch back to the workflow editor window with this user interface, and we choose new from the file menu. And it removes all the modules. And then we start our workflow by reading in some data. And we want to read in data in COVICE format. And for that, we choose the read COVICE directory module. Not the read COVICE module that we just had in our workflow, but read COVICE directory. And for that, I go to the module browser here on the right. I click the arrow on the read category so that it opens up and shows all the modules in this category. And I press on the read co-vice directory module, do not release the mouse button, and drag it over here to this canvas where you can see the workflow that I have already built. It should be empty now when you start, and release it here by releasing the mouse button. And it should open up, and when you select it, the right part of your window should switch from the module browser to a tab named parameters read co-vice directory. If it's not working for you, yeah, and you have to select it by clicking on it. So the selection works by clicking on it, and you can see the menu that you have selected. It's surrounded here by this pink rectangle. And you can modify the parameters of this module that you have selected. And we have to choose the directory from which it should read the data. So please find the directory parameter and click the folder icon that you find there. And then we navigate in the window that opens up here from the root folder to /data. And within the data directory, please go to the Vistle subdirectory. It's a little bit above the bottommost screen. And there you have a fourth subdirectory. And there you have a tiny subdirectory. And this is the directory that you should choose. Data, Vistle, course, tiny. And we open that by pressing the choose button. And now we get offered to choose files that we want to read in for the various parts of our data set. And we start with reading in the geometry of the data set. So we need to make the geometry available as the grid for the data set. So we choose the grid parameter, and in the choice list that you get offered, we choose the tiny_geo. Does everyone see this possibility to choose tiny_geo? And open the correct folder. And this is a volumetric three-dimensional grid. That is something that our renderer is not able to show directly. So we start by adding modules which give us a glimpse onto this data. One module that we can use is the bounding box module. It will create an axis-aligned bounding box around the data, which surrounds the data tightly. So we go to the map category in the module library, choose the bounding box module. It's the first in the map category, and drag it over to our workflow editor area. And now we have to connect it to our read-co-wise directory module. And the read module outputs the grid on its first output port. First means counted from the left, and the output port is a port at the bottom of the module. So we click on that port, drag the mouse while holding the button clicked onto the leftmost and topmost input port of bounding box, and while being on top of the red input port, we release the mouse button, so we establish a connection from output of the reader to input of the bounding box module. And you see that you have established a connection if a black line appears connecting those two ports. And this line will enable data to flow from output to input. And if we execute our workflow, the bounding box module will update its parameters according to the size of the bounding box that it found around the data. And we can also show the bounding box inside our render window. And for that, we need to get a renderer. And we find the renderer in the render category of the module browser. And we use the cover renderer. And we drag it over. And as soon as I drag it over to my workflow, it opens up a new window. I switch back to the workflow editor, and now I also build a connection from bounding box to the renderer, and I use the output port from bounding box at the bottom and connect to the input of the renderer. And I re-execute the workflow, this time by clicking the reload icon in the renderer. And this executes the workflow. You can use the view all button again. And here I see the bounding box. And in order to get an idea where it is situated in space, I can switch on the axis in the view options menu, show axis, and switch that on. And then I get a coordinate system of unit length arrows, and the RGB arrows correspond to the X, Y, and Z coordinates. And you see the length of the bounding box, it's about 2.5 units or so. Okay, so that's the first thing that we saw about the data. But we want to see more. Let's have a look at the shape of our computational domain. For that, we use the domain surface mapper module. And this time I'm going to search for it. I move the mouse cursor into the filter line here on top of the module browser, and I type in domain. And after filtering according to this criterion, only the domain surface module remains. I use that, drag it over to the workflow area. And I connect that to the same output of the reader. So I feed in the grid into the module, and I connect the output to the renderer. The first output counted from the left, and I execute my workflow, and now I see the shape of the domain that we have. You can look. Susanne is a little bit frightened that Vistle might crash, rightfully so. So in order to not lose what we have built so far, let's save our workflow. We have a.
Mine actually crashed.
It already happened. Okay, sorry, too late for you. Perhaps Susanne can help you rebuild your workflow quickly. And all the others, please use the save button, for example, in the toolbar, and it will bring up the file browser, and you can navigate to your home directory and type in, for example, tiny.vsl as file name and save it right into your home directory. And if you're also unlucky and if your session crashes, you can reload that workflow from there. Please remember to press the save button from time to time. Now we have the outer shape of our computational domain here in the 3D render window. And in the render window, we will go to the view options menu again. And first, we will switch off the axis. And second, we will change the draw style from as is to wireframe, so that we get a bit of an idea of what the cell structure looks like in this three-dimensional domain that was used for this simulation. So here each triangle corresponds to the outer face of a cell in the computational domain. And the domain surface module also has another output, which gives us some feature edges of the domain. And when we execute the workflow from there and switch view options back to as is, you see that the edges have gotten an additional line in the computational domain. And when you want to use the outer shape of the computational domain as context for your visualization, you want to be able to view inside the domain. In order to do so, we need to cut it open. And for that, we have the cut geometry module. And we find it by filtering for cut geometry. Then we drag it over. And we put it into our workflow in between the left output of domain surface and the renderer. And in order to remove the whole outer shell of the domain, we need to remove the connection directly from domain surface to renderer. In order to remove a connection, please rest your mouse cursor on top of the connection and double click it. And it will go away. And we execute the workflow again. And then we see just part of the outer surface remaining. And let's change what remains by interacting with the module. So now we use the Vistle menu of the render window. And there we have an entry for this cut geometry module. And we select the pick interactor. And when this pick interactor is checked, it shows this little arrow here. You can move it, and it will move the plane which is used to cut through the shell. So you can move it if you click a straight line on the arrow. You can change the orientation if you grab the arrow tip and move that around. Then move the arrow tip so that cuts away the, in this case, bottom part of the domain. Switch that by another 180 degrees. It's not so easy. And then move it up a little bit so that I get an image similar to this one. So this provides some context for my visualization, and I can still see what's going on inside. And now we're not depending on the bounding surface any longer. It doesn't provide an additional clue in this case. So I switched back to the workflow editor, and I cut the connection between bounding box and renderer as well. So now we have established some context, and could everyone follow so far? Then let's move on to visualize fields which have been computed. We have two kinds of fields available here. And let's start with the scalar field. And the scalar field that we are interested in is the pressure field. So we select the read co-wise directory module by clicking on it. And if it's the only one that is selected, it will show the parameters for this module. And we will change the field 0 parameter from none to tiny_p for pressure. And this lets us read in the pressure, and we start with adding an additional module for visualizing the pressure. So we start with creating an isosurface which selects all the points where we have a certain pressure value, and we drag over the isosurface module from the library to the workflow and connect the second output of readCover's directory to the isosurface input, so the first input on the left top.
Why the second pin? Why not the third one? Because it's the third one in the list. How do you know that you have to connect?
Which pin do you mean?
So if you click on read Covise directory, and then the third option is field 0, not the second one. The second one is normals.
Okay, that's because these normals are mapped directly to the three-dimensional grid, if you have any. So they are attached to the output of the first port.
Okay.
And to the output of all the other ports indirectly as well, because every field carries the grid where the field exists with it.
But in principle, the order of these elements corresponds to the order of the bits.
Yes. If you rest your mouse cursor on the second output of read Covise directory, you will get a tooltip and it should read what's going on. Doesn't come up again. Just before it read field 0 out. So there you would see the relationship again. Yeah, so we configured field 0 to be tiny p, and that should be available from the second output port. And we connected to the first input of isosurface, and the isosurface output we connected to the renderer. And then we execute the workflow again, and the isosurface module computes the isosurface for its ISO value, which is configured by default to 0. So that is what we see here in the render window. And we have two ways to interact with that. In order to do so, we go to the Vistle menu in the renderer, and I start with using the slider. So here the slider lets me modify the value for which the isosurface is computed. And you can see how the isosurface changes its shape when you modify this value. That's one way of interacting with the isosurface. The other way is a pick interactor mode. So I enable that, and it brings up this sphere, and I move this sphere into the data domain, inside the data domain. And when I do so, it will look up the data value that it finds at the position of the sphere and compute the isosurface to the data value that it has found there. And this is a nice way of interacting with the isosurface, especially from a 3D virtual environment.
You see what the value is.
If you want to see the value, you need to go to the isosurface menu. It will show it there. You can also leave the menu on screen. If you click the dashed line at the top of the menu, you can see the value more easily.
Oh, yeah.
It will enable to tear off the menu.
Yeah.
Keep it on screen. So isosurface indirect volume visualization level sets, that's a first technique for visualizing scalar fields. Now we explore a cutting surface, and for that we get the cutting surface module from the library, and we add it to the workflow, and we connect its first input to the pressure field on the second output of read co-wise directory. And we connect the output of the cutting surface module. That means the first output to the renderer. And it should cut through the data at some location. You can see it here. And now we need to get colors onto the cutting surface. For that, we need a color module which establishes a color mapping for a pressure field. So we add a color module to the workflow. We connect it to the second output of read co-wise directory as well. And we connect the second output of color to the color renderer. And from the parameters, we choose a different mapping, for example, plasma, than the default cool, warm, cool mapping. Then we execute our workflow. And now the cutting surface that I see here changes colors. And I can also move that cutting surface around. So that I see I cut throughout here the flow as it goes along the channel.
How did you move the cutting surface?
How I moved it there by, sorry, I didn't explain it. Going to the Vistle menu, choosing cutting surface, enabling the pick interactor for the cutting surface. And perhaps it would be wise to disable the other pick interactors in order not to get confused by them. So I disable the pick interactors on cut geometry and isosurface. Now I can move around the cuts. And I can also bring up a legend for the color map. If I choose the colors submenu from this, go to the color tiny p submenu and click show. Now I can see the correspondence between color and data value. It would also have been possible to color the isosurface, and I do so by connecting the second input of isosurface as well with this pressure output, so that the pressure data gets mapped onto the pressure isosurface. What's going on here? I execute the ISO surface module. I did that by double clicking it. And now I have an ISO surface that is colored in one uniform color, because we colored the ISO surface according to the attribute that was used to extract it. So it has to have one color by definition. And as I change the value, you will always see that the color of the isosurface corresponds to the color that you find on the cutting plane through the pressure field.
Can you show again what modules did you connect?
Yes. So here the reader is wired up to the color module for establishing the color mapping from pressure value to RGB values. That's the second output of read co-vice directory that is connected to the input of the color module, and also the cutting surface module here gets its first input connected to the pressure output, and all the inputs of the isosurface module are connected to the pressure output.
Okay, thanks.
And I would say so much for visualizing scalar fields. Now let's continue to the velocity vector field. In the workflow editor already, so that's good. And I want to read in the velocity field on the field 1 port. And so I go to the parameters for the read co-vice directory module, and I choose tiny velocity from the choice list for the field 1 port. And we start by employing our scalar field visualization techniques to this vector field as well. And we use a cutting surface module and a color module. And we wire that up to the third port of read co-vice directory. And if we do so, it will just use the magnitude of the vector for these operations. And so I switch on the additional color map that I have now. It's the tiny velocity color map. I disable the cutting surface interactor for the pressure plane and enable it on the velocity plane. Cut here. Perpendicular to my other cut. Now I see colors which correspond to the magnitude of the velocity vector field. Okay, nothing new. One unique technique for getting a glimpse of the vector field is the vector field module. It draws lines corresponding to the direction and length of the vector at every point that it receives as its input, and I feed the output of the cutting surface module into the vector field module. And I connect the vector field module to cover. And let's see what's happening. So now we see these lines, which are a little bit long, which follow the direction of the velocity that it finds at the position where this line starts. Let's make them a little bit shorter. You can do so by making the scale value of the vector field a little bit smaller. That's 0.2. And you see that the attachment point is the bottom. So that's why the lines start right on the position where I cut through the velocity field. And if I move the cutting plane around, the lines will move together with the cutting plane. Okay, lines are nice, but arrows would be even nicer. And we can use the thicken module to transform the lines into arrows. So we get the thicken module from the module browser, drag it over to the workflow, and connect the output of vector field to the first input of thicken. And we connect the first output of thicken to the input of cover. I re-execute the workflow by double-clicking on the cutting surface module. That was actually wrong to directly connect the thicken module to the renderer. Only our ray tracing renderers can render tubes directly. We need to transform the tubes to triangles. So I insert a two triangles module in between the tubes and the renderer. And I remove the connection that I established wrongly. Now I re-execute it. And now I recognize nothing because the tubes are so thick. I make them less thick by changing the radius parameter of the tubes of the thicken module from 1 to, for example, 0.01. I re-execute by double-clicking the cutting surface. That looks more reasonable, but it's still a little bit thick. So I dial that down to 0.005. And I also want to get arrows. So I change the end style in the thicken module from open to arrow. We execute by double-clicking the cutting surface module. And now I have arrows that point in the direction of the flow. Yeah, if we wanted to have color on them, we could input the color into the vector field module and forward that to cubes module, and then we should get colored arrows. And the color corresponds to the velocity magnitude. Okay. Arrows which point in the direction of the vector field. Another possibility to visualize the vector field is the tracer module, which computes paths of massless particles which travel along the flow. So we add the tracer module to the workflow. I scale the workflow down a little bit by pressing the control key and turning the mouse wheel so that I can see all of the workflow. Replace the tracer, connect the third output of read co-wise directory with the velocity field to tracer input. And I connect first output port of tracer to cover. And we execute the workflow, and let's see what. Now I need to configure the seed points for the tracer, where it starts to compute the particle paths. And for that, I enable the tick interactor for the tracer. And from this very menu, I also increase the number of start points. 30. And it shows a line with spheres on both ends. And the seed points for a tracer are lined up in a regular distance on this line. Move it a little bit up so that it is on top of my cutting plane. And I disable parts of the workflow that I built so far. So I remove the cutting planes through the pressure field, and I also remove the vector field so that I get a clearer view of just the tracer. So here we see the streamlines that are computed, and for that it integrates the way that a particle takes with the flow forward and also where it came from backward. There are a couple of parameters for this tracer module. The most important ones are configuring the seed points and of the number of seed points, and there's also some limits for the integration. The maximum length of the path that should be integrated, the maximum time of the path that should be integrated, and the maximum of integration steps that it should take. And here I can change the direction, the t direction in which the trace is computed. Initially it was set to both. And we could also configure it to forward, so that it just computes the traces in the forward direction, starting from the seed points. And also here, tubes look nicer than just lines. So I add another thicken module. Together with a 2 triangles module. And I remember from before that a good value for the radius was 0.005. So I typed that in already into the radius parameter for the new thicken module. I execute the pipeline. And now I have these lines showing the streamlines for the flow in this channel. I switch back to the render window, and now I change the task type from streamlines to moving points. And then it replaces the streamlines with animated particles. And the number of steps that it outputs there is too large, so that for a very long time nothing happens. And I can reduce that by reducing the time for which it computes the traces to, for example, 4 seconds. Then the animation will start over again earlier. And because in our workflow path from the tracer to the renderer, we also have this thicken module inserted. We see spheres for the points that the tracer actually outputs there. And yeah, that's another way of doing vector field visualization. So yeah, these are the most basic techniques for doing scalar and vector field visualization. We have a small tutorial prepared in our documentation, which works on the same data set and which also has some additional things that you can do with this data set. But so much for now.